Might be a good idea to write it down. Okay, so we'll start out with something basic here. 2 to the third. What does it mean when you raise something to an exponent? What does 2 to the third really mean to do? Yep, James.
Multiply it by itself.
Right, in this case, yeah, the 2 is multiplied by itself 3 times, right? So 2 times 2 times 2, we know that's 8, right? Okay, and so then by that same argument, right, 2 to the second, well, that's going to be 2 times 2, so that makes sense, it's 4. And then 2 to the 1, well, it's just 1, 2, right? So it's just going to equal 2. Right? And so that definition works, right, when we first kind of start understanding exponents, but then when we get to weird stuff like 2 to the 0, you know, it's like, how do you multiply something by itself 0 times? And so that definition kind of falls apart a little bit, but it's still helpful when we're talking about, you know, just positive, you know, whole number exponents. But another thing we can observe here, okay, to kind of help us understand, you know, what 2 to the 0 is looking at the pattern from what happens as we lower our exponent by 1. So each time we lower our exponent by 1, what happens to the value of the answer here? It divides by 2, or it's half of it, right? So we can see, you know, like divide by 2, and so then, you know, again, lowering our power by 1 more here, 1 to 0, it would make sense to say, okay, well, we'll divide this once more by 2, which results in 1, which is correct, right? 2 to the 0 power is 1, right? 5 to the 0 power is 1. Pi to the 0 power is 1, right? 0 to the 0 power, that's actually indeterminate form. Okay, we don't know what that is, but in some cases, right? But anyway, so this also then, following that kind of pattern of every time you lower the exponent by 1 and then dividing the previous answer by 2, follows even into the negative exponents. We can kind of use that idea here as well. So for example, 2 to the negative 1, what's that equal? 1/2, right? Which is just 1 divided by 2. Okay. 2 to the negative 2. What's half of 1/2? 1/4, right? Which is also the same thing as saying 1 over 2 squared. So there's that whole idea of if you have a negative exponent, you can kind of move it into the denominator and give it a positive exponent. Okay? And then so on and so forth, right? You could do 2 to the negative 3, 2 to the negative 4, whatever. You can kind of see what's going on here. Okay? So there's kind of the origin of some of at least the integer exponent rules that we have, right? Some of the ideas there. Or not origin, but maybe a way to see it. And that nice little pattern that, you know, I think maybe shed some light on some interesting things. All right, some other things we want to remember, too, when it comes to exponents. Okay, right? If you have 2 to the third times 2 to the fourth, all right? Well, again, we can go back to James's definition here to help us simplify that. Some of you guys maybe already know, okay, 2 to the seventh, right? But let's just take a look at this, right? 2 to the third, as James defined it, that's 2 times 2 times 2, right? 2 times itself 3 times. 2 times 4, 2 to the fourth, sorry, is 2 times 2 times 2. 2 times 2 times 2 times 2, sorry. 2 to the fourth. But really, when you take 3 2's and multiply them by 4 2's, you really just have 7 total 2's there, and so that's why we can say it's just 2 to the seventh, right? And so there's the idea of adding exponents, right? When you multiply numbers at the same base, you can add those exponents. 3 plus 4 gives us 7. Okay. Likewise, if we take like 2 to the third and raise it to the fourth power, 2 to the third to the fourth. Okay. So what do we do here? Well, now, right, again, we can kind of use James's little definition there. 2 to the third times 2 to the third times 2 to the third times 2 to the third, right? 2 to the third to the fourth, that means 2 to the third 4 times. Well, now since we're just multiplying those 4 things together, right, just like we did in number 1, we're multiplying here, we can add those exponents. They all have the same base, so we can add the exponents. 3 plus 3 plus 3 plus 3, 2 to the 12th. Which, of course, is the same thing as just taking 3 and multiplying by 4 there, right? So a power raised to another power, you multiply to simplify. Okay. 2 numbers, when you're multiplying, you add their exponents to the same base, you add the exponents, but when you're power to a power, you multiply the powers. Okay. And then one more here. 2 to the fourth divided by 2 to the third. All right, well, again, writing things out. 4 2's in the numerator, 3 2's in the denominator, and then what can we do to simplify this? You can cancel, right? 1 pair, 2 pair, 3 pairs. And so we're left with 2, or 2 to the 1. Which is the same thing as really doing what with the exponents? Subtracting, right? 4 minus 3 gives you 1 there. Which makes sense, right? If when we multiply, we add the exponents, right? 3 plus 4 gives us 7. It makes sense that when we divide, then, that we should subtract those exponents. 4 subtract 3, 2 to the 1. Makes sense, right? Okay. So again, let's just review some simplifying here. Okay, so we'll do some examples, just to make sure we're okay. And we'll just do 2 examples, and then we'll look at 2 graphs, too. Okay, so let's say you've got 2 to the negative 9th, all over 2 to the negative 7, times 2 to the negative 5. So the good news is, they're all the same base, all the base of 2, right? So, well, let's see here. In our denominator, right, in our numerator we only have 1 term, so that's kind of good. In our denominator we kind of have 2 things being multiplied together, so let's try and put those together here. So since we're multiplying, what should we do with our exponents? Add them. So you get 2 to the negative 12. And now that we're dividing, right, 2 to the negative 9 divided by 2 to the negative 12, what should we do with our exponents now? Subtract. So negative 9, and if you want, you can even write this like 2 to the negative 9 minus negative 12, if you want to. Like, you can even write it like that. Okay? Just to help yourselves out. Which is really then plus positive 12, and so it becomes 2 to the 3rd. Or, if you really want, 8. Okay, let's try another one. Questions on any of that so far? Straightforward. Okay. We'll try another one here. A over b squared to the negative 2 times a squared over b to the 3. Now, the things with exponents, I think part of the difficulty of some of these exponent problems is that you can kind of go a couple different paths and still end up with the same answer, and so that can be kind of confusing because one student might want to go one way and another student might want to go another way, and so lots of different paths here. So it's really kind of up to you what you want to do, right? Some people may see this negative 2 exponent and want to do the reciprocal of this thing to make it then to the positive 2, so make it like b squared over a to the positive 2, and you can do that. I'm going to do it a different way, though. I'm going to distribute the exponents to start out here. So when you distribute that negative 2 inside here, it's going to become then a to the negative 2 over b to the, what power should b have in the denominator here? Negative 4, because it's like a power being raised to a power there. That's right. And here for the second one, a to the 2, but that's going to be cubed, becomes a to the 6, and then b to the, well, you can put a 1 in there, right? b to the 1 to the 3 becomes b to the 3. And now we have 2 fractions, and we can multiply by multiplying across the top, multiplying across the bottom, right? So a to the negative 2 times a to the 6 combines to become a to the what? 4. Very good, right? We're adding the exponents now that we're multiplying the bases. And here we're multiplying the bases. We're going to add these exponents to get b to the negative 1. Okay? Typically, in simplifying, leaving a negative exponent is not simplified then. So while we may not see much more to do here, when it comes to simplifying, typically that means no negative exponents. So this b to the negative 1, we can do, you can kind of think of it a couple different ways. One way to think about it is just b to the negative 1, since it's a negative exponent, you can move it up into the numerator, and this becomes positive now. Okay? If you have a negative exponent in the numerator, you can move it to the denominator to become positive. If you have a negative exponent in the denominator, you can move to the numerator to become positive. The reason why that works It's because this is really equal to a to the 4th over 1 over b. But of course, having a fraction within a fraction there, we don't want that. So we can multiply by its reciprocal, b over 1, which is just b, which then results in that in the first place there, okay? So that's the idea. Questions on any of that? Again, this is mostly a review, that's why I'm trying to go through it kind of quickly here. I know, some of us feel more confident in our exponent, properties than others, so, but there's some of the properties illustrated there. Okay. Questions on any of that? Whoops. Okay. All right. Now we're going to talk about exponential functions. Okay. So we're going to define an exponential function to be f of x equal to a times b to the x power, where b is not equal to 1. Why, if we're talking about exponential functions, do we not want b to be 1? Why do we even say that? So what?
If b is 1, it doesn't matter what the exponent is.
Exactly, right. If we have b 1, 1 to the x is always going to be 1, regardless of what number you plug in there. And so really it's just going to be a constant function, right? It's not really exponential if b is 1. Likewise, we also have to further stipulate b also must be greater than 0. For a similar kind of reason. Well, actually, it can't be 0 for a similar reason that it can't be 1. If b was 0, well, then it would be 0 to the x, which again would just be 0. Then times a would be 0. And so again, you'd have a constant function. And if b was negative, well, then you'd have a really weird function going on there, because there would be values of x that if you plug those in would then suddenly make your graph imaginary, right? For example, if x was like 1/2, taking a negative number and raising it to the 1/2 power, that's imaginary. But then suddenly at an x value of 1, the function would become real again. So it would like jump from real to imaginary depending on what x values you're plugging in there. So, that's no good either. So we want to just stipulate that b has to be greater than 0 but not 1 as well. Okay, so that results in two different shapes. We're going to look at cases where b is greater than 1. I guess I should say. Let me do it this way. b greater than 1 case. Okay. So look at the cases where b is greater than 1, and then we'll also look at the case where b is between 0 and 1. Okay. The different b values result in different graphs there. All right. So let's look at the function f of x equals 3 to the x. And consider that. Okay. To graph this, we're not going to worry too much about trying to. There is essentially a parent function here that you'll get an understanding of what that looks like. Once we kind of see a few examples here. But let's make a table and just see what happens. Okay, and we want to pick low numbers because with exponents things get out of control real quick. 3, I guess. Okay. So let's start pretty easy here. We'll start with 0. So if x is 0, what is y, or what is f of 0 going to be? If that's our function right there, what is f of 0 going to be? 1, right? 3 to the 0, which is 1. Okay. If we plug in 1, 3 to the 1, it's 3. Right? Plug in 2, 3 to the 2 is 9. And then plug in 3, 3 to the 3 is 27. So you can see these numbers get out of control real quick. Plug in -1. What's 3 to -1? 1/3. 1 over 3. Yeah, 1 over 3 to the 1. Okay. What's 3 to the -2? 1 over 3 squared, or 1/9. Yeah. So you can see we jump really quick from jump really quickly from large numbers, right, on the right hand side there, the 27. The next one would be 81, and then we jump real quick down to teeny tiny numbers, 1/3, 1/9. Okay. So these graphs. Okay. So if you go and graph this, All right, I'm going to count by 5s on my y-axis. And then just 1s on the x-axis. All right, we plot these points. Okay, so we get 0, 1. Okay, so 0, 1 with the eyeball that one because, you know, something like that. And then 1, 3, that's a little bit more. And then 2, 9. And then 3, 27. And then, of course, -1, 1/3, you really have to eyeball. And same thing with the 1/9 as well. Ooh. Talking about end behavior here, right? What happens as x approaches positive infinity? What's our function approach as x approaches positive infinity here? Positive infinity, right? Goes up forever. As x approaches negative infinity, as we go further and further left, what does our function value approach? 0, right? So this is an interesting situation. We have infinite behavior on one hand, but then it approaches the number 0 on the other hand, right? Yeah, so depending on which infinity you're approaching here. All right. So then we can discuss the domain of this thing, right? What would the domain of this function be? Negative infinity to positive infinity. Yeah, there's no problem with any number. We can plug in any number of 1. You can say all real numbers there too. Another idea. What would the range of this function be? 0. Now, I kind of assumed here, should we include the 0 or not? Do we ever actually get to 0? No, right? We're just going to approach it. So the limit approaches 0, but we're never actually going to get there. Okay. All right. X-intercepts. So since our range never gets to 0, what can we say about our x-intercepts? There are none, right? What about our y-intercept here? It's 0, 1, right? 0, 1. So we do have a y-intercept. Okay? So that's for values of b greater than 1, which makes sense, right? If you have 2, 3, 4, 5, 6 raised to an exponent, that number, as you raise it to positive exponent, is going to get bigger and bigger and bigger. And that number, as you raise it to negative exponent, is going to get smaller and smaller and smaller because it's going closer to 0 that way. All right? But let's look at what happens when we have b between 0 and 1. Okay, and see what happens there. So, of course, so 0 less than b less than 1 case. So we're talking like 1/2, 1/3, 1/4, those kind of things. 2/3, right? Okay, and let's just say our function in this case is going to be 1/3 to the x. So again, let's make a table here. Okay, and again, we'll go from like -2 to 2, or something like that. Again, you want to pick 2 big numbers, or too big a number, because it's going to just get out of control. All right, so again, we'll plug in 0. 1/3 to the 0 power is 1. Okay. 1/3 to the 1, 1/3, right? 1/3 squared, what's that? 1/9, right? Yeah, 1/3 times 1/3. What about 1/3 to the -1? Yeah, it's the reciprocal of 1/3, so it's just 3. It's 3 to the 1. Okay. What about 1/3 to the -2? It's going to be 9. Okay. Again, the idea there being, right, 1/3 to the -2 right? That's the same thing as saying then, 3 over 1 to the positive 2. You can just reciprocal. You can do the reciprocal of that fraction there. And so you get 9. That negative exponent just makes you do the reciprocal of whatever you're, whatever's being raised at negative power. Okay, so we look at the graph. Bless you. Okay, I'll count by 5s again on my y-axis. So. Again, I'll count by 1s again on my x-axis. So. And plot these points here. So negative 2, 9, negative 1, 3, 0, 1, and then again it kind of goes something like that. So there's the graph of 1/3 of x. So now we can see some things change, right? What's the domain? Still going to be all real numbers. Okay, the range. Zero to infinity, yeah, it gets a little funky when you change the order on it. It's still 0 to infinity, right? The lowest y value is still going to be approaching 0, right? And then it goes up to infinity. So all this really did is reflect our graph over the y-axis there, really. All it really did. Speaking of that, the last thing I want to talk about here is transformations. Okay, of an exponential function, and then we'll be done. And I'll just list some things here. So we'll say, oops, sorry. Not a times x. We'll say a to the x plus h. Okay. That will shift things left or right by h units. Okay. And it's kind of it's like in the opposite, okay? It'll go left if h is greater than 0. It'll go right if h is less than 0. Okay? It's kind of the opposite like that. That same idea we've seen before, right? If h is greater than 0, we shift things to the left. We shift right things if h is less than 0. Okay? So it's kind of the opposite idea of what, again, that same kind of idea you've seen before in other transformations and stuff. If we take a to the x and we add a k outside there, how will that shift things? Up or down, right? So shift up or down by k units. Again, up if k is greater than 0. So now this is the case where it is the intuitive kind of sense there. If k is greater than 0, you shift up. If k is less than 0, you shift down. Okay. Then we have other things too. If we have negative a to the x like that, negative on the outside, that's a reflection over the x-axis. Okay, and then if we have f of x equal a to the negative x, that's a reflection over the y-axis. Okay, so all those transformation ideas still come into play here. Okay, all those transformation ideas, same ones you've seen before with other parent functions. So that's a good thing, right? Which would explain then why 1/3 to the x If we rewrite that, right, that's 3 to the negative 1 to the x, which is really then 3 to the negative x. So you can see here 3 to the negative x. Compare that to this earlier graph, which is just 3 to the positive x. So this graph, if you reflect it over the y-axis, gives us this graph, right? It's the same thing, right? This is the negative x there. That's the reflection over the y-axis. Okay? So, well, that's it. All right. So you get 7 or so minutes to take a look at any last-minute things there on your review if you want, or at least copy down this homework assignment. Okay. Of course, I'll put the homework assignment on Google Classroom if you want to get right into looking at the review and stuff too. That's fine. The rest of the time is yours. I know it's not very much, but we did get the chance to go over some things earlier too. Page 224. Numbers 13 to 16, 20, 23 to 25, and 40. So that'll be the homework. Due, obviously, next Monday or whatever. Okay. We'll go over this homework on Friday. Okay. I'll tomorrow is going to be the test. We're not going to look at the solutions to this tomorrow. We'll look at the solutions to it on Friday. Okay. So there it is. There it is. Okay.